You ever wonder how your calculator just knows the square root of some crazy number, like instantly? Or how engineers manage to design these incredibly complex lenses? Well, it turns out the answer is this really elegant trick from calculus. It's all about the power of knowing when something is close enough.
So here's our game plan for this explainer. First, we're going to build some intuition by literally zooming in on a curve. Then we'll turn that idea into a powerful mathematical shortcut. We'll even put it to the test with a real example, see how it's used in fields like physics and optics, and finally, we'll wrap up by looking at a new way to talk about this whole concept using something called differentials.
All right, first things first, we have to build our intuition. And believe it or not, it all kicks off with a really simple observation about curves. So if you look at the graph of a function from way back, you see exactly what you'd expect, right? You see all of its bends and its twists, but this is where the magic of calculus comes in with a fascinating question. What if we just pick a single point on that curve and we just start zooming in, getting closer and closer and closer to it?
As we get closer, something really interesting starts to happen. The curve, well, it seems to flatten out. That bend becomes less and less noticeable.
And this right here, this is it. This is the foundation for everything we're about to cover. This simple observation that any smooth curve becomes locally linear when you get close enough is the idea that powers some incredibly complex calculations.
Okay, so we've got this core idea that a curve looks like a line up close, but which line is it? That's what we're going to figure out next, as we turn this cool visual insight into a really practical tool.
So that straight line we just saw, it is of course the tangent line to the curve at that specific point. And we're going to use this tangent line as a kind of stand-in, or an approximation for the curve itself, as long as we don't wander too far away from our point.
And here's the formula for it. Now, I know it might look a little intimidating with all those letters, but don't let the notation scare you. This is really just the equation of a line. All it's saying is that our approximation, that's L of x, is just where we start, f of a, plus the slope at that exact spot, f prime of a, times how far we've moved away. It's a recipe, plain and simple.
And using it is just like following that recipe. You pick an easy-to-calculate point, a, that's near the number you actually care about. Then you find the value and the slope right there, and then you just plug all those pieces into the formula we just saw. That's it.
So we have the concept, we've got the recipe. Let's actually put it into practice and see how this amazing shortcut can solve a problem that would be pretty much impossible to do in your head.
Yeah, I definitely don't know this off the top of my head. 3.98 is just an awkward number. But here's the thing. We know it's really close to a much friendlier number, 4. And the square root of 4, that's easy. This is the perfect setup for a linear approximation.
All right, let's follow our recipe. Our goal is the square root of 3.98, so our function is simple, f of x equals the square root of x. What's a nice point A that's close to 3.98? Well, that's easy, it's 4, so a equals 4. The value of our function at a is f of 4, which is just 2. Now the derivative, the slope, is 1 over 2 times the square root of x. So at our nice point a equals 4, the slope is 1/4. We have all of our ingredients.
And now we just plug those ingredients into our formula. Our custom-built approximation is L of x equals 2 plus 1/4 times the quantity x minus 4. You can think of this as our own little machine for estimating square roots right around the number 4.
So let's use our machine. We plug in the value we actually care about, 3.98. That gives us 2 plus 1/4 times 3.98 minus 4, which simplifies down to 1.995. And just like that, we have a fantastic estimate for the square root of 3.98. No calculator needed. And just look how accurate that is. The actual value is 1.99499 and a bunch of other numbers. We were off by less than a 10,000th. That's incredible. And as you can see in the table, this works for other nearby values too. The closer we are to our starting point of 4, the better our estimate gets.
You know, this is way more than just a cool party trick from mental math. This concept is actually a cornerstone of how we simplify and solve incredibly complex problems in science and engineering every single day.
Just take this quote from our source material. In optics, when scientists are dealing with light rays at really shallow angles, they replace these complicated sine and cosine functions with their simple linear approximations. This simplification is literally what makes designing things like camera lenses possible.
Seriously, the applications are everywhere. Calculating the swing of a pendulum, designing bridges, and yep, even powering the very algorithms inside your calculator that seem to find answers like magic. They're all using this fundamental shortcut. So for our final piece, let's look at a slightly different way to frame this exact same idea, using the language of differentials. Now, this isn't a new concept. It's really just a powerful notation that focuses on the change between the approximation and the real thing. So we define this thing called the differential, dy, as the slope of the tangent line, f prime of x, multiplied by a tiny little step in x, which we call dx. And if you remember that the derivative f prime of x is just dy over dx, you can see this is just a simple rearrangement of that same core idea.
So here's the key takeaway. We have the actual change in the curve, we call it delta y, which can be really hard to calculate, and then we have the change along the straight tangent line, dy, which is super easy to calculate. So we use the simple dy as a stand-in for the complex delta y.
Think of it like this. If you take a little step dx to the right, delta y is how far the actual curve went up or down. dy is how far the tangent line went up or down. And as we saw from our zoom-in trick at the beginning, when that step dx is really, really small, those two values are going to be extremely close to each other.
So from the tangent line to the differential, it's all about the same thing, using a simple, straight line to understand a complex curve. This powerful idea of approximation, of accepting that close enough can be good enough, is a fundamental tool that powers so much of modern science and engineering. It really makes you wonder, doesn't it? Where else is this principle the secret key to solving the impossible?